This is Lecture 2 on gravitation and black holes. Every body with mass has a Schwarzchild radius. You can calculate it with the formula. When the size of the body is larger than its Schwarzchild radius, it is not a black hole. It is any ordinary body, such as a star, a planet, a baseball, a nucleus, a proton, etc. We can, if we wish, use the general relativity correction formula for these bodies, such as for the Earth. For a massive supergiant star that exploded as a supernova and left a collapsed core with more than a few solar masses, that core was too dense for its collapse to stop at being a neutron star. Its collapse density and pressure were too high for neutron degeneracy pressure to support, and it collapsed to a size smaller than its Schwarzchild radius. Once this occurred, it was a black hole, from which neither light nor matter can ever escape, and it will remain a black hole forevermore. Most likely, the collapsed core was rotating, which we covered late in the course. But if it was not rotating, then it continued to collapse rapidly to a single central point of nearly zero size and infinite density. It might not be zero size, but the entire mass is believed to have collapsed to much smaller than the size of a single proton, perhaps even to the Planck length of 10 to the minus 20 times the diameter of a proton. Physicists do not have a verified theory of quantum gravity to know the physics at the central point. General relativity and known physics tells us what occurs right up to the central point, but not at the central point. When the size of the body is smaller than its Schwarzschild radius, it is a black hole. The mathematical spherical surface at the Schwarzschild radius distance from the central point, where the non-rotating mass has collapsed, is called the event horizon of the black hole. Any matter or light that reaches the event horizon of a non-rotating black hole from the outside will then plunge to the central point of infinite density and never escape back to our universe. These are called black holes because light and matter cannot escape. Anything happening inside the black hole event horizon cannot affect events outside of it. The singularity is extremely dense, but the rest of the volume of the black hole is empty space, vacuum, whose spacetime is extremely curved and light does not escape. We always refer to the mass of the black hole, but it is actually the amount of mass energy of the black hole. This increases when matter crosses into the event horizon or when light crosses into the event horizon. The energy of the light photons increases the mass energy of the black hole. Once matter or energy crosses the event horizon, the black hole does not preserve any memory of what crosses the event horizon, other than its mass energy and its electrical charge, which we will not cover. A black hole is a mass energy singularity cloaked from our universe by an event horizon. No shell observers are possible at or inside the event horizon. In a 9-minute supplementary video, you can see that Newtonian mechanics actually gives the correct formula for the Schwarzschild radius when we set the escape velocity equal to the speed of light. In 1783, scientist John Michell proposed dark stars, actually supermassive black holes, from which light cannot fully escape and he identified how to find them. However, the classical picture of these dark stars is not the correct picture of black holes. The supplementary video also covers the gravitational potential energy, which we don't need in the main course. Later we will learn what it is like to plunge through the event horizon and what happens inside the event horizon. Do not assume that the event horizon necessarily kills the astronaut or that it is any kind of material wall. It is a mathematical surface in curved spacetime and vacuum. The physics for rotating black holes is more complicated than for non-rotating black holes. We will cover the interesting aspects of rotating black holes late in the course. But until we get to that point, every result that I present applies specifically to non-rotating black holes or bodies. Probably all black holes rotate to some extent, but if they rotate slowly, the result for a non-rotating black hole may suffice. If you like, when I say non-rotating, you can think slowly rotating. Let's look at the column to the right of the neutron star. A stellar mass black hole of 10 solar masses. A black hole has no material radius, but its Schwarzchild radius, determined by its mass, determines the characteristics of spacetime in the vicinity of the black hole. The Schwarzchild radius is 30 kilometers for the 10 solar mass black hole. According to Newtonian gravity, the gravitational acceleration at that Schwarzchild radius is 6 billion times more than at the surface of the Sun. However, we must use the general relativity correction, and that is infinite at the Schwarzchild radius. Let's imagine a shell observer standing on a shell 50 meters outside the event horizon. At that radius, the general relativity correction factor is 24, not infinite. And the gravitational attraction for the shell observer is 130 billion times more than the Sun's surface. Later we will calculate that a human shell observer should stay 4 million kilometers away from this stellar mass black hole in order to survive, about 6 solar radii. Astronomers have detected a couple dozen stellar mass black holes in the Milky Way, but there are thought to be hundreds of millions that have not been detected. Stellar mass black holes could represent as much as 1% of the ordinary mass of galaxies, according to a recent article. You might think about how to detect a solitary black object that is not emitting light. Astrophysicists believe that star collapse cannot produce black holes with less than 2.1 solar masses. We take 100 solar masses as the top end for a stellar mass black hole. So these are stellar mass black holes. So stellar mass black holes have Schwarzchild radii of 6 to 300 kilometers. Stellar mass black holes in our galaxy can sometimes be detected when they have a binary companion star, which we won't cover, or when they merge with a black hole or neutron star and emit gravitational waves, which we cover late in the course. Conditions early in the Big Bang might have produced black holes with any value of mass. These are called primordial black holes, though sometimes this term is used only for small masses, smaller than stellar mass, whose Schwarzchild radii could be very small, even smaller than the size of a proton. Small primordial black holes have never been detected and might or might not exist. If primordial black holes exist, they could be part of the unseen dark matter mass of galaxies. Black holes are believed to lose mass energy via a process called Hawking radiation and eventually evaporate, which I cover in a 12-minute supplementary video. The time to evaporate is proportional to the mass times the third power. Stellar mass black holes would take many orders of magnitude longer than the age of the universe to evaporate, and actually they're all gaining mass by absorbing the cosmic microwave background radiation. A primordial black hole with the mass of the Great Pyramid of Giza would evaporate in less than 1,000,000 years. So lower mass primordial black holes that might have been created in the Big Bang might have evaporated by now. But masses over 200 billion kilograms could still exist. Supermassive black holes. At the center of almost every large non-dwarf galaxy is a supermassive black hole, acronym SMBH. Beware, SM means supermassive, not stellar mass. In this radio image, each white dot is believed to be a distant supermassive black hole devouring material at the heart of some galaxy millions of light years away and emitting radio waves. Supermassive black holes have a mass of hundreds of thousands of solar masses to millions to billions to 66 billion solar masses. As massive as these supermassive black holes are, they are much less than the stellar mass of their galaxy, and even more so that galaxy's dark matter. So don't think of the black hole mass as overwhelming the galaxy, or even the central bulge of the galaxy. The supermassive black hole at the center of the Milky Way is named Sagittarius A star and is 4 million solar masses versus 1 trillion solar masses for the galaxy. Its Schwarzchild radius is 12 million kilometers, or about 18 solar radii, or 1/5 of Mercury's orbit. Imagine 4 million suns collapse to a black hole inside Mercury's orbit. Instead of extreme brightness and heat, we would see a huge black disk 27 times wider than the Sun, as we will learn later in the course. The Earth could still remain at its orbital distance, though that orbit would only take 4 hours instead of a year. Dozens of stars closely orbit the Milky Way supermassive black hole in a space comparable to our outer solar system, where our comets live. The large grid spacing in this plot is 1/10 of an arcsecond, so about 900 times the Earth's orbit, or about 1/100th of a light year. In place of comets elliptically orbiting the Sun with periods of thousands of years, these are stars orbiting the Milky Way supermassive black hole here at the center, with periods of 10 to 100 years. Now, these star orbits have been imaged in infrared light, and some have been tracked over complete periods. These star orbits tell astrophysicists the mass of the supermassive black hole, 4 million solar masses, an upper limit on its size, it is a black hole, and that its rotation is less than 10% of the theoretical rotation limit. So far, the closest approach of a star has been about Saturn's orbit, so the general relativity correction factor is small enough that Newtonian mechanics mostly suffices, and these are nice Newtonian ellipses, though with precession due to general relativity. Perhaps you would like to think about how astrophysicists calculate the mass of the supermassive black hole in our neighbor, Andromeda galaxy. Stars are very densely spaced in the galactic core. The gravitational impact of the supermassive black hole gets dwarfed by the billions of other stars in the galactic core beyond about 10 light years. Beyond the central bulge of a spiral galaxy, dark matter's mass dominates over the mass of stars. So please don't think that galaxies are attracted to one another due to their central supermassive black holes. Their effect is insignificant at those distances. This column is the Milky Way supermassive black hole, Sagittarius A star. 4 million solar masses. This is its Schwarzchild radius. For a shell observer standing on a shell 50 meters outside the event horizon of Sagittarius A star, the general relativity correction is 16,000, not infinite, and the gravitational attraction for the shell observer is 200 million times more than the sun's surface, 600 times less than for the stellar mass black hole. Later we will calculate that a human shell observer should stay 3 billion kilometers away from this supermassive black hole in order to survive, so about Uranus's orbit. For a shell observer standing on a shell a small height above a black hole's event horizon, the general relativity corrected gravitational acceleration experienced by the shell observer is approximately inversely proportional to the square root of the Schwarzchild radius or the mass. A supermassive black hole of 1 billion solar masses, which is this column, is 10 to the 8th times more massive than a 10 solar mass black hole, this column, and the gravity experienced by a shell observer near the event horizon is about 10 to the 4 times less, as we see in this table. This number is about 10,000 times less than this number. This gravity is also approximately inversely proportional to the square root of the altitude above the event horizon. There's half as much gravity 200 meters from the event horizon versus 50 meters, with altitude calculated from reduced circumference r coordinates, as we will learn later. Astrophysicists do not know how or when supermassive black holes began to form. They probably began before stars began to condense and shine, and did not form from mergers of stellar mass black holes. They may have formed while galaxies were first condensing, or they may have begun in the first seconds after the Big Bang. They may have formed first from early dark matter concentrations. A small minority of astrophysicists propose that our supermassive black holes existed before our observable universe underwent a big bounce instead of a Big Bang. Certainly, supermassive black holes have merged when galaxies have merged, and certainly supermassive black holes have fed on nearby gas and stars. The mass of a galaxy correlates with the mass of the central massive black hole, central supermassive black hole, and astrophysicists do not know why. Smaller than supermassive black holes, intermediate mass black holes with hundreds to thousands of solar masses may exist at the centers of globular clusters or in galaxies. Astronomers have a few such candidates. These might have formed from mergers of stellar mass black holes, or were black holes that fed at the centers of dwarf galaxies. It could be that early intermediate mass black holes merged to form the precursors of the supermassive black holes. There is a very good 13-minute video describing the size range of black holes and how they were formed at this link, which will be in the lecture script PDF. Quasars and accretion disks, Part 1. Black holes look black, right? When does a black hole not look black? A black hole may have an accretion disk consisting of dust, particles, and gas in orbit outside the event horizon. A large accretion disk can be a light year in diameter. Collisions, friction, and electromagnetic interaction between particles cause the material to slowly lose orbital potential energy and heat up as it cascades inward through a sequence of stable orbits and then spirals into the event horizon. The accretion disk heats up, ionizes into a plasma, generates its own strong magnetic fields independent of any electrical charge on the rotating black hole, and emits infrared light, visible light, ultraviolet, often X-rays, and sometimes gamma rays, all of which propagate to the universe and we can see. The most luminous, powerful, energetic, continuously radiating objects in the universe are quasars, emitting as much light as 100 trillion stars. These are rotating supermassive black holes in galaxies far away and long ago that were actively feeding on infalling matter, an accretion disk, and radiating away as light, something like the sun's rest mass energy each year, or the Earth's rest mass energy every minute. In addition to hydrogen and helium, the infalling material includes elements formed by nuclear fusion in early stars. In this artist's representation, the red, orange, yellow, and white accretion disk is gas spiraling in toward the event horizon, the black hole which is too small for us to see there, heating up in the process and emitting light. The white jet to the upper left is matter that has been ejected relativistically just short of the event horizon. For an actual quasar, the brightness would be so many orders of magnitude brighter than shown that it cannot be represented. The quasar is more luminous than the rest of its galaxy combined. These distant emissions were first detected in radio waves and seemed to be as small as stars, not galaxies. These were called quasi-stellar radio sources, or quasars. Subsequently, it was found that about 90% of quasars are radio silent, so they are called quasi-stellar objects, or QSOs. These are also called active galactic nuclei, or AGNs. More than 1 million quasars have been observed, versus 2 trillion galaxies in the observable universe. It may be that all supermassive black holes at the centers of galaxies were quasars feeding for tens or hundreds of millions of years early in the life of their galaxy. The Milky Way supermassive black hole has a low mass accretion disk totaling about the mass of Jupiter that extends about 1,000 astronomical units, or 1/100th of a light year. Some of the stars with close approaches to the supermassive black hole plow through the accretion disk. Our supermassive black hole is not presently a powerful quasar. The quasar closest to the Milky Way is 600 million light years away. We will learn more about accretion disks late in the course after we learn about rotating black holes. Human shell observer. A human cannot survive the 28 Gs of being a shell observer standing stationary at the surface of the sun, much less a white dwarf, a neutron star, or close to the event horizon of a black hole. This says nothing about surviving a free-fall plunge into the black hole, which we will cover later. In terms of gravity, not radiation, a human shell observer could safely stand about 2 solar radii from the sun. A white dwarf, or a neutron star. But 6.3 solar radii from a 10 solar mass black hole. 19 astronomical units from the Milky Way's supermassive black hole, about the orbit of Uranus, and 300 astronomical units from a billion solar mass black hole. Orbiting observers and plunging observers are in free fall, weightless, and can safely get closer to the black holes, as we will see. General relativity. Gravitation is a force. Gravitation is an acceleration. Classical Newtonian mechanics is sufficient for these if we don't get close to a neutron star or a black hole. Gravitation also bends space-time and changes how time proceeds, the ticking of clocks. Einstein's general relativity describes these. General relativity extends special relativity. All observers in the universe measure the same value for the speed of light in vacuum, and matter can never reach that speed. I would like to give you a brief introduction to an appreciation of general relativity broad strokes, but don't worry about following the math in detail. We want to see the landscape of what general relativity covers without getting bogged down or anxious, but actually we will be able to derive a correct result for how time behaves. This is Einstein's general relativity field equations that he published in 1915. If we read the equation left to right, on the right side we have matter, energy, momentum, and pressure, and they are telling the space-time curvature on the left how to curve at each point in space-time. Reading the equation right to left, the space-time curvature on the left-hand side tells the matter, energy, momentum, and pressure on the right-hand side how to move in space-time. All elementary particles, whether massless or with mass, with rest mass, matter or antimatter, light photons, respond to the local curvature of spacetime. This is a tensor equation representing 16 coupled nonlinear partial differential equations indexed by the Greek subscripts mu and nu. This is very complicated, but fortunately, two important tractable cases are known that greatly simplify the situation. It was not Einstein who discovered these two tractable cases. The second case to be discovered is where all matter and energy in the universe are distributed uniformly, homogeneously, isotropically, through all space in the universe at all times. This is the basis for physicists' understanding of the expansion of the universe starting from the Big Bang. We will not cover this in this course. In 1915, while serving in the German Army in World War I, physicist and astronomer Karl Schwarzchild solved Einstein's field equations exactly for the case of a single, spherically symmetrical, non-rotating mass with zero electrical charge. This is the basis for the solution for black holes, stars, and planets, and what we will be using. This was later extended to include electrical charge, which we will not cover at all. The properties of the black hole do not depend on other conserved elementary particle quantities, such as baryon number and lepton number, whose memory is not preserved by the black hole. In 1963, the solution was discovered for a rotating symmetrical mass. We will cover rotating black holes later in this course, after we understand non-rotating black holes. Until we get to that point, every result that I present applies specifically to non-rotating black holes or masses. Probably all black holes rotate or spin to some extent, but if they rotate slowly, the result for a non-rotating black hole may suffice. If you like, when I say non-rotating, you can think slowly rotating. We will get a little taste of the Schwarzchild solution before it gets too involved for this course. Don't worry about any math details that you don't follow. We'll come back to measurable phenomena. Following is the time-like Schwarzchild metric for curved spacetime for a non-rotating spherically symmetrical mass distribution. For example, a star or a black hole with zero net charge. This formula is the Schwarzchild metric for motion in a plane that contains the center of the mass distribution. The left-hand side, d tau squared, is a quantity directly measurable by a real observer, but the quantities on the right-hand side are formed from global coordinates that may or may not be directly measurable by real observers as follows. D tau on the left-hand side is the short elapsed wristwatch time between two events, two light flashes, for some specified observer, a shell observer, a plunging observer, an orbiting observer, for which the two events occur at their location and a short time interval apart. So it's a wristwatch time. dt on the right-hand side is the elapsed clock time between the two events as measured by a stationary, far-away observer very far from the gravitating mass. R is the reduced circumference R coordinate. It is the measured spherical shell circumference divided by 2 pi. R sub s is the Schwarzchild radius of the star, black hole, or central mass, 2 gm over c squared. Phi is the polar angle in the plane containing the mass and the observer. We'll only care about that when we talk about orbits. Don't worry about what this metric means. We will do 2 examples to learn more. This metric can be used for a black hole outside the event horizon. This metric can also be used for stars and planets as long as we restrict r to be greater than or equal to the body's radius, capital R, which is greater than its Schwarzschild radius because the body's not a black hole. We cannot directly measure the R coordinate by walking off distance from the center of a black hole with a measuring rod. We can't measure it for a star, and we can't measure it for the Earth. For a hypothetical spherical shell, we could walk one circumference, measuring as we go. Then we divide the circumference measurement by 2 pi, and we use that as the reduced circumference value as our R coordinate for that shell. For black holes, stars, and gaseous planets, we imagine an advanced civilization building a super strong spherical shell at constant distance from the massive body, and we get the R coordinate from measuring the circumference of that shell, at least in principle. We imagine that each shell is labeled with its R coordinate. This gives us a starting point, and later we'll learn about the stretching of space due to the gravitating mass. In reality, no material is strong enough to construct a shell close to a black hole's event horizon. No material can withstand the crushing gravity. The time between two events. First, we choose to explore the time between two events, two light flashes. And so we use the time-like metric that we given above. Then we specify the particular observer whose wristwatch time we're interested in. We will care about 4 observers. a stationary faraway observer located so very far away from the central mass that local spacetime is essentially flat, not curved, there. A plunging observer, who is plunging radially toward the central mass in free fall, so weightless. We will take the simplest case where the observer started from rest infinitely far from the central mass, even though this case would take infinite time to get close to the central mass. An orbiting observer in a circular orbit around the central mass. We will not ask how the observer got into the circular orbit, nor investigate whether they can ever safely get out of that orbit and get away from the black hole. A shell observer, who maintains a fixed distance and position from the central mass beyond the Schwarzchild radius outside the event horizon. We adopt the imaginary theoretical fiction, though often impossible in practice, that an advanced civilization has built a concentric spherical shell surrounding the central mass and the observer is standing on the shell, thus shell observer. Alternately, the shell observer could be in a theoretical rocket ship maintaining stationary position by blasting suitable rocket exhaust toward the central mass with the observer's feet toward the central mass. Results will always be the same for the faraway observer and a shell observer at infinite distance from the central mass. The reason why we need 4 observers is that their measurements of space and time will be different from one another, shockingly different in some cases. So every time we use the Schwarzchild metric, first we identify which observer's wristwatch we want to look at. We will learn that spacetime is curved due to the presence of masses. The metric tells us how to interpret the measurement of 2 events, light flashes, that are extremely close in time and space, so we can represent the time difference between the 2 events as a time differential and the space separation as a spatial differential. So d tau is the differential wristwatch time of our chosen specified observer. Let's choose a shell observer stationary on the shell at our coordinate r around a massive body, whether a black hole, a star, or a planet, with Schwarzchild radius r sub s, and let there be 2 rapid light flashes initiated d tau apart according to the shell observer's wristwatch, sourced from a stationary source at the shell observer's location. Since the light flashes are initiated at the same location, dr is going to be 0 and d phi is going to be 0, so our time-like metric for this case becomes simplified as follows. d tau shell observer squared equals 1 minus r sub s over r times dt far away squared. And we could take the square root and we can rewrite this with dt far away on the left hand side. dt far away equals d tau shell observer divided by the square root of 1 minus r sub s over r. For a stationary shell clock, for the stationary shell observer, not moving. What does this result mean? Well, we're only interested in we can only have shell observers who are further than the Schwarzchild radius they're outside the event horizon. And in that case, 1 minus r sub s over r is between 0 and 1. And 1 over that square root is greater than 1. This means that dt far away is a specific amount greater than d tau shell observer. The time between shell flashes measured by the faraway observer is longer than the time between flashes measured by the shell observer, where the flashes originated. While the shell observer experiences 1 second of time, the faraway observer experiences a longer time interval. Time passes more slowly for the shell observer than for the faraway observer, faster for the faraway observer. The shell observer ages more slowly than the faraway observer. This is time dilation, similar to but different than the time dilation of special relativity. This is gravitational time dilation. In special relativity, motion is relative and symmetric, and each observer sees the other's clock as running slow. With gravitational time dilation, there is a difference between observers, and the effect is not symmetric. We could calculate the clock difference between two shell observers on different shells by referring each to the faraway observer. A clock closer to a center of gravitational attraction, down the well, runs slower than a clock farther away, up the well. More time elapses for the distant outer shell observer than for the inner shell observer. Gravitational redshift. This graph shows the gravitational redshift of light between a shell observer and a faraway observer. SH means shell observer and far means faraway observer. We can learn about how light behaves in this gravitational field. Let the shell observer shine blue light up toward the faraway observer. Here's a shell observer at the surface of a star, shining blue light up toward a faraway observer on a planet. We let d tau shell observer be one period of the sourced blue light, t shell. The light received by the faraway observer will have a larger value of dt far and period t far away up here in the numerator. All observers in the universe measure the same value for the speed of light. This is true for general relativity as it is for special relativity. Light wavelength lambda equals the speed of light times the period of the light. Therefore, the faraway observers measure a larger value for the received light wavelength than does the shell observer for the sent light wavelength. The wavelength has increased as the light photons traveled from down well to up well. For visible light, we say that the light has been shifted toward the red, which has longer wavelength than blue. The light has become gravitationally redshifted, and moving away from the massive body. The energy of each photon is inversely proportional to wavelength, so the photons have lost some energy in climbing out of the gravitational well. Shortly we'll look at some redshift amounts on Earth. If light were sourced by the faraway observer and shined or shone toward the shell observer, our equations show that the light becomes blue shifted and traveling down the gravitational well. Wavelength decreases and photon energy increases. For a 10 solar mass black hole and an imaginary non-human shell observer 50 meters above the event horizon, when the shell observer shines visible light radially outward, a faraway observer sees the light redshifted by a factor of 24. So visible light becomes infrared. If the faraway observer shines visible light radially inward, this shell observer sees the light blue shifted by a factor of 24. So visible light becomes ultraviolet. The effect increases without bound for shell observers approaching the event horizon. The effect increases for an imaginary shell observer 50 meters above the event horizon of a more massive black hole, such as a supermassive black hole. Although it is relatively easy to understand and remember the gravitational redshift and blue shift of light, do not think that this gravitational effect only affects light. It is the passage of time that is different for shell observers at different distances from the massive body, and is an effect of the curvature of spacetime due to the central mass. Congratulations, you have used Einstein's general relativity to solve a problem in physics with curved spacetime. Gravitational redshift. Time passing differently for two observers who are stationary with respect to one another is evidence that this spacetime is curved and requires general relativity to solve. If the central mass were zero, the Schwarzchild radius would be zero, the ratios above would be 1 for all observers, time would pass identically for all observers that were stationary with respect to each other, spacetime would be flat, not curved. In that case, the metric would equal the Minkowski metric for flat spacetime in that case, and Einstein's special relativity would suffice for solving problems. According to general relativity, a higher clock runs faster, a lower clock runs slower for stationary shell observers. However, according to special relativity, a speeding clock runs slow, and both effects apply. On Earth, the gravitational redshift is extremely small but measurable. The gravitational redshift was first verified on Earth in 1959 by Pound and Rebka at Harvard. They sent gamma rays with a precise energy vertically downward 20 meters in a tower to a very selective detector. The photons' energies were gravitationally blue shifted by a ratio of 2.5 times 10 to the minus 15. And their ingenious experiment used upward motion to precisely offset the blue shift such that the photons would be detected. In 2021, a physicist measured the 10 to the minus 19th difference in clock rates over 1 millimeter of altitude. For GPS satellites, the general relativity speedup of the satellite atomic clock, due to its altitude above the Earth's surface, is 6 times larger than the special relativity slowdown of the clock due to its orbital motion. GPS satellite atomic clocks run faster than Earth surface clocks by 38.7 microseconds per day. For the GPS system to work properly, each satellite intentionally reduces its counting of atomic clock periods to match Earth surface time, taking special and general relativity into account. When GPS satellites were developed in the 1970s, the Air Force and its contractors were uncertain whether the scientific advice on the general relativity time rate correction was correct, or even whether there was such an effect. The first satellite included a switch to include the correction or not, and it was quickly found that the correction was needed and was correct. The results above were specific to shell observers and do not apply to an observer plunging toward or into the black hole. They experience space-time differently than the shell observer, even at the same location and time. We will examine a plunging observer later. The different passage of time for different shell observers and for the faraway observer is one effect of the curvature of spacetime due to the central mass. Examining distances will help us to better understand spacetime curvature.